Good afternoon, everyone, and thank you for attending our webinar today. My name is Rebecca Hirschfield. I'm with Babel Street, and we're very happy to have you for our program on why word embeddings and semantic similarity are mission critical. It's now my pleasure to introduce Kafir Bar, Chief Scientist from Babel Street, and he'll be introducing these concepts and telling us more about semantics. Kafir, over to you.
Thank you. Thank you so much. Thanks for the introduction. I'm very happy to be here. So once again, I'm Kafir. I'm the Chief Scientist at Babel Street. And for today, I'm planning to introduce word and text embeddings for semantic similarity, and also to talk about related topics and why they're so important for many deployments of systems that analyze text. So let's start with text similarity, and let me take you back to Rosetta Stone about 2,000 years ago. And Rosetta Stone has a text written on it in ancient Egyptian and also in ancient Greek. In fact, ancient Egyptian text is written here in two different scripts. One is hieroglyphic and the other one is demotic. And there are only some minor differences between the three versions here. So we can safely say that those three texts are close enough in meaning so that we can say that they're similar. A more, I would say, flexible definition for text similarity is semantic similarity. And semantic similarity refers to the task of comparing two pieces of text and returning a number reflecting how similar the two texts are. So let's take an example here. I can eat ice cream all day, right? That's probably going to be similar in many contexts to I can eat chocolate ice cream all day. Since both statements are about eating an ice cream, right? So that's obvious. It's just that on the right side, the statement is a bit more specific. But what about this one? I can eat chocolate all day. So now it's not about ice cream. And I would say that they're still very similar because they talk about like eating dessert all day, right? So in that sense, they're still semantically similar. But then we have this text. I don't like chocolate, if there is someone here who would say that. But the question is if it's similar, it's to I can eat chocolate all day. And some of you will probably say no, because there is a negation there, which obviously changes the meaning of the statement completely, right? But we can still say that those two expressions are similar somewhat, because they're both talk about liking or disliking chocolate. And it makes them more similar to each other than to other statements that talk about completely different things like weather condition, traffic, whatever. So it really depends on the context and the downstream application that we are using semantic similarity for. Okay, where do we use semantic similarity in natural language processing applications? I want to start with an example. So let's say we're lucky enough and we decide to go on vacation, and the first thing to do is to book a hotel to accommodate us during our vacation. And to find a hotel, I usually go to one of those hotel review websites, so that I can read reviews, written by previous guests. And I typically use keywords for finding relevant reviews based on my personal interest. And for me, it's all about noise. I like quiet places. And so I'm using the word noisy here, so I can find reviews that talk about noisy rooms, noisy places, noisy hotels, and so on. All right, so when I use the word noisy, I may retrieve those reviews, right? For example, it's very noisy at night, hotel is so noisy, and there's this one too, probably the other direction. The security guy said that we are too noisy and so on. But this is very helpful. We can get many such reviews, but using this simple exact matching technique, we probably are going to miss many other important reviews, such as those ones, right? It took me a while to fall asleep because of the noise, and there was a loud sound, and the other one has electric hammer drills and so on, right? So those words or indicative words are keywords, right? And they're highlighted in red here. And we want to retrieve those reviews based on semantic similarity between those keywords and our word in the query, which is noisy in our case. Therefore, we want something, technology that will compare such keywords using kind of a fuzzy matching technique, resulting in a score assigned for every pair of words. In our case, noisy will be one of those words in the pair, and then one of those keywords. And the score should reflect how similar they are. So noisy is probably very similar to noise in many contexts. I mean, one is noun, one is adjective, but they refer to the same thing. So they will be assigned, let's say, with a very high score of 90% similarity score. And then we have sound, right, which is also similar to noisy, but probably less than noise, hence the lower score, 75%. Then we have drills, and drills and noisy will be 50%. This is just, I invented those numbers, but they kind of make sense. And I added here a few random words like car, table, cake, just for reference. And they should be considered as less similar to noisy than all the others, as you can see here. But how do we do that, right? How do we calculate this number? And I mean, words like noisy, noise, or any other words, they're simply just symbols, right? They don't have characteristic information about their meaning that we can use in order to calculate this score. So the modern approach for calculating semantic similarity is to give those symbols a mathematical representation first, and then use this mathematical representation to calculate the similarity. And we have to make sure that the mathematical representation captures the meaning of those words. And the traditional way of doing this is by looking at the words that co-occur with each word in our vocabulary, and using a large collection of documents, usually referred to something like that as a corpus. So let's take a closer look at how it is usually done, but that's going to be more intuitively than in real life, since in real life there are more things that go into this calculation, which I'm not going to talk about here. So what you see right now, it's something that we call co-occurrence matrix, and for every word in our vocabulary, we have a row and a column. And it's a pretty, as you may realize, it's a pretty large matrix, right? Because, I mean, our vocabulary might be huge if we're using a large corpus. But here we only see a very small portion of that matrix, just for reference. And the way to generate this matrix is by simply counting how many times each word co-occur with the other words, and co-occurrence is limited only to a very small window surrounding the word in context, the word in focus, I would say, like 2 words before and 2 words after. So for example, first row here on the left, we count 10 times when the word very is mentioned close to the word noisy in our corpus. And the word to appears 12 times in the same window of noisy, and so on, right? So it's fairly easy to generate this matrix, and all we need is just a large corpus of documents. They don't need to be annotated, the documents, right? We don't need them to be annotated. It's just plain text. That's it. That's all you need. But I'll do say that the genre topics that are mentioned in those documents may affect the shape of this matrix, the numbers in this matrix, and that's important, right? Because it may change the meaning or the way that you can calculate semantic similarity between words. Okay, so word vector is basically just one row of this matrix, right? So the vector of noisy, for example, is just the first row here. And the vector tells us a lot about the meaning of the word noisy. Intuitively, words that have similar frequencies of words that co-occur in their small window are also similar in their meaning, right? If you think about this, if you take two other words, let's say a car and a truck, so they're probably going to have at scale, right? They're probably going to have many words that co-occur in the same context of those two words, car and truck. And that makes sense. If you take a large enough corpus, you may be able to capture these statistics. So mathematically, a vector is just a list of values, as you see here, and each value represents one dimension, right? So this is how we call it. And it means that we take those vectors and we embed them in multi-dimensional space, right? Where each one of those numbers is just one dimension in that multi-dimensional space. For example, you can look at a map, right? And here we have two dimensions. We have latitude and longitude, and each location is represented by a two-dimensional vector of two numerical values. And like you can see here in New York City and Paris. And we can calculate the distance between the two cities using their latitude and longitude values using mathematical formula as simple as Euclidean distance, if you're familiar with this, or anything more sophisticated than that takes more information into account, such as traffic information, weather condition, public transportation availability, and so on. Here we use only two dimensions, right? But technically speaking, we can use multi-dimensional vectors as many as we want, right? In our case, it's going to be a huge number of the size of the entire vocabulary, which can get to millions sometimes. So what is the best way of calculating the similarity between two word vectors? Whatever their dimensionality is. One known formula is called cosine similarity. As I mentioned before, Euclidean distance is probably pretty standard to use when we calculate the distance between two cities. And for word vectors, just pretty standard to use cosine similarity. However, there are other functions that can be used. Don't worry about the math here. It's only for reference, and I'm not going to go over everything right now. But all it does is measuring the distance between the two vectors, taking into account as many dimensions as you want by simply measuring the angle between the two vectors and then normalizing that by the magnitude of the vectors or their original length. It's considered as standard, as I say, in the field, and the result, the number that you get back, reflects the similarity between the vectors, and since we believe that those vectors capture the meaning of the words, so that number reflects the semantic similarity of the two corresponding words. But again, I'm not going to dive into the math here. I'll just say that we typically assume that the two vectors are normalized, which is not always the case. It's just an assumption. It's a safe assumption, mathematically speaking, which means that those two components here, mathematical components, they are equal to 1. And basically, cosine similarity becomes as simple as dot product between two vectors. So those of you who are not familiar with dot product or linear algebra, don't worry about this. And it's just basically multiplying element-wise, multiplying the vectors element-wise and then summing the result. So the result, the example here is like 10 times 2 plus 12 times 5 plus 10 times 13 and so on. Then you get just one number. And that number is the similarity score between the vectors. If it's high, it means that they are more similar. Okay, so now if I go back to this and we'll look at the vectors again, we can notice that, or we can think that, when we add more information into the vector by adding more dimensions, right? We may think about this as, an increasing level of information. So we add more information, which is probably a good thing. However, it's not always the case. And when we add too many dimensions, we're going to need to have a larger corpus to support, the statistics that we collect from it. And also we're probably going to require more computational power to calculate cosine similarity, because now it has more dimensions. If you do that at scale, trying to calculate cosine similarity between many vectors, you're just gonna add more calculations into your into that formula. So instead of working with vectors of the size of the entire vocabulary, we use different techniques to compress those vectors to something more reasonable. And for example, 300 dimensions, that's a number that people usually use, but there are other numbers too. And the classic approach is to use a model, a neural network such as Word2Vec or GLOV, which we train for or using the same corpus I mentioned before. And I'm not going to cover all the details right now, but I'll say that this technique is considered one of the major breakthroughs in the field of natural language processing in the last decade or so. And each dimension of the 300 dimensional vector, which is the result of this process, is now a combination of many, or mathematical combination of many of the original dimensions, which makes it a very a powerful representation, compact representation of each individual word. And like with the original vectors, we can still use cosine similarity with those vectors, and it's limited to 300 numbers, and that's it. And then this is a great achievement. Now, the vectors that we get, they capture the meaning of the words, as we said, and the process that we just described using Word2Vec, for example, makes them vectors that you can do even more things. So apparently, you can also use them with simple arithmetic operations, which align well with semantic manipulation. So, for example, you can take the vector of the word Japan and then subtract from it the vector of Tokyo. Now you do that element-wise, right? So you subtract the first value and then the second one, the third one, and so on. You get a new vector. And now intuitively, the vector that you got is probably, it represents a country without a capital city. And then we can then add the vector of Berlin, Germany's capital city, and you suddenly get a new vector that is similar to the vector of Germany. And that's pretty cool, right? Because intuitively, this is exactly the mathematical operations that we used here. They're aligned pretty well with how we think about those words semantically. So you can do more stuff like that, right? So I just added here another example that I thought about. But there are many examples. This is called analogy test, and you can go online and find tools that are already designed to help you write equations like that, and you get back the results and looking at different outcomes, and that's pretty interesting. yeah, so not only that, of course, you can calculate, as we said before, semantic similarity between a given word and then, like here, fish, to all words in the vocabulary. So if you have millions of words, you can basically calculate constant similarity between that word, input word, and then everything else. And then you can show here only the 10 best results or K best results. And so you get like the most similar words to the word fish. Okay, so now we only covered the creation of such vectors for a single language, say English, right? But we can do that for other languages, right? It's language agnostic, this process, but then we would need to use a corpus of documents written in the other language. But then we will get, vectors for that language. What about multilingual vectors, right? So technically speaking, if we create a set of vectors for each language individually using Word2Vec, those vectors are not necessarily aligned with each other. For example, the word car in English and coche in Spanish will not have the same or similar values in their vectors, and they're probably not going to be similar, or they're not promised to be similar. And that's a problem if we want to use vectors for different languages, especially if I search the reviews, the hotel reviews websites, and maybe I want to get reviews written in other languages too. And so yeah, so we need to think what to do with this. By the way, a comment before we move to the next slide. Here we present the vectors as two-dimensional vectors, right? It's a two-dimensional space, but usually, as I said, we're working with 300 dimensions. It's just more difficult to show that on the screen. Okay, luckily there are ways to align those vectors together to look something like that. So they have the same spread, right? They the two spaces here, they look similar. They have the same structure, we call this also the two spaces align. And the way to do that is, there are different ways of doing that, but one traditional way is to use a relatively small dictionary of the two languages. Say here in this case, it's English and Arabic. You don't need many dictionary entries. Something like 5,000 will do just fine. And then you use those words in the dictionary to align the two matrices here. So one matrix here is just if we take all the vectors one language, let's say English, we put them like as rows in this matrix, one next to each other. And basically we have a matrix, and we do the same for Arabic, right? And then we align those words that we know from the dictionary. And then we can calculate using mathematical tools, we can calculate a transformation, a mathematical transformation, and apply it to the to all the other vectors. And usually we do that on one language. So we apply the transformation to, let's say, the Arabic vectors, and then we get them closer to the English space. So in fact, we're making we're modifying the Arabic vectors, not the English one, and modifying them in a way that they will be closer to how the same vectors or the vector of the same words will be positioned in the space of the English language. Okay, so so far we talked about how we generate vectors and how we align together vectors from different languages, and how we use them to calculate semantic similarity using cosine similarity. And by the way, when we do what we just described, multilingual vectors, now when we calculate cosine similarity of vectors of, let's say, car and coche, they will have the same, or they will be very similar to the cosine similarity score that you will get for similar words in English, which is pretty cool. Okay, now I want to we want to get back to our use case or search engine use case. Because this is how we started, right? And remember, we wanted our search engine to return reviews with words that are similar to our query word, which is noisy. And now we want to use vectors so that we can retrieve those reviews here on the screen. And the traditional way, I would say, to index documents without vectors in a search engine is by breaking the text into tokens. And a token is usually referring to what we defined as a word. Obviously, it depends what language we're talking about, right? Because English has a relatively poor morphological system. There are languages with much richer morphology. So it depends how we define a token. But then once we have tokens, we index the document based on each individual token. And then exact match search is carried out by efficiently finding documents that were indexed with the query word. And there are efficient ways to do that. And but it becomes slightly more complicated when there are more than one token in the query. But let's leave this for some other time. But how are we gonna use this for when we have vectors for semantic similarity or semantic search? So we said before that we know how to generate a vector for every word in our vocabulary. So let's say we know how to do that. We have vectors. Now we want to use them during search. The way to do that, remember, in order to match two vectors, we need to calculate cosine similarity, right? So a naive way of doing that is, instead of indexing the document with all those vectors, we simply store the vectors of each individual word just like that, without indexing, and then refer every vector to the original document. And then when, during search, we take the vector of the query word. We know how to generate this, in our case, noisy. And we calculate cosine similarity of noisy with all those vectors that we have in our search engine, right? So everything that we stored for every review, that could be a huge number. And, depending how many reviews we indexed in the system, that could be very, very slow, like prohibitively slow, since, this way we would not be able to perform hundreds of floating point operations to figure out the cosine similarity of the query. So this is a problem, right? I mean, when dealing with a large database, it's not like a challenge. It's a problem. This is totally intractable. So we cannot do that. But luckily, there are better ways to do that. But before that, if you are looking closely at the Python implementation of cosine similarity, you will realize that, given two vectors here, v1 and v2, I showed you before, right? We go over all elements of both vectors, and we multiply them and then sum those values into what we define here as similarity. And the loop here will take, let's say, 300 operations, because let's say we have 300 dimensions in each vector. And this is just for, just two vectors. And when we have many of them, it's just going to be many operations to run. Okay, so we have other ways to do that, efficient and better ways to do search with vectors. And if you think about this, we can, when we calculate cosine similarity for the query word and each individual vector in the index, we always get a similarity score, right? So, like a similarity value. It doesn't matter what vectors you take. You can, when you calculate cosine similarity, you'll get a value. Some of those vectors, some of those pairs will get like a very small value, and some will get a high value, a large value. And then we want to choose only the top let's say 10 words, right? Or generally speaking, k words or k most similar words. And k is just a variable we can configure. And this is, I mean, usually people refer to these algorithms, the naive vector search algorithm, as KNN, or k nearest neighbors. And it means that we are looking for the k closest words to the query word under the definition of the distance function, or the k most similar words, neighbors. Now, there are approximate KNN algorithms that rearrange all these vectors in that data structure that enables us to do like a fast lookup. I'm not going to go over all the details how to do that, but it uses some sort of a tree structure. And but nothing comes for free. Those algorithms cannot they cannot promise that the results will be 100% accurate. And there's going to be some level of error introduced to this process by this approach, which we'll have to learn how to live with. Approximate KNN is an active research area, and there are many algorithms and libraries that you can use, which introduce different alternatives, definitions, and all of them can be configured to prefer speed to over accuracy and vice versa. And this figure is taken from the link below. It compares speed versus accuracy of many such approximate KNN algorithms. I'm not going to go over the details of this figure right now, but it clearly shows that the accuracy level is inversely correlated with speed. And we see that when those algorithms are configured to perform fast lookup, the accuracy is relatively low. And when they are configured to run slower, the accuracy improves. So it really depends on how we want this algorithm to perform. But many open source search engines, such as Elastic and Lucene, they already come with their own version of approximate KNN, which you can use out of the box to start indexing vectors, right? You just need to bring your vectors and you can start working with this. Okay, so far we talked about how to create vectors for individual words, which we can then use for semantic similarity. But what if our query has more words than just a single word? Or what if we want to combine all words of every review into one vector, and then captures the compositional meaning, right? The composition of the individual word meanings. So a simple approach is for aggregating vectors of individual words into one vector that represents the entire text, is to average the individual word vectors element-wise, one by one. But typically every text has some content words in it and some functional words. So content words are typically like words like nouns, verbs, adjectives, and so on. And functional words may be prepositions or the definite or an indefinite article, and so on. So we should probably consider content words as more important than functional words for representing meaning. And what we can do to improve this, because here in this approach, you basically don't. I mean, you consider all words in the same importance level. And what we can do to improve that, we can assign we can use some kind of a weighting function to assign weight for each individual word according to its importance to the meaning of the text. Anyway, I'll skip the details for now, but there are different ways of creating those weighting functions, and it can be very effective. Once we have those text vectors, this is how we call them. Text vectors are vectors that refer to like a complete text, not necessarily just one word. We can use those vectors using cosine similarity the same way, right? So we can take vectors that represent documents now, and we can calculate the similarity between the documents. And this is very effective for search. Now, weighted average is a rather simple approach for calculating text vector. Some other techniques, and especially those that are based on language models, such as BERT or GPT or T5, and those models are becoming the state of the art for many semantic natural language processing tasks. However, using such models at scale introduce many challenges, since they require a strong computational power and like strong machines, which is hard to comply with in real life, especially when you want to install the software on-prem. Anyway, relaxing those computational requirements is an active research area these days. And of course, at Babel, we invest a lot in this field. So before we conclude our session today, let me cover a couple of use cases for where our NLP platform Rosette is using vectors. So let's start with this one, name matching. So in our name matching offering, where we calculate how similar two names of organizations are. We use vectors to calculate semantic similarity between content words, which are part of the names, like here, right? So using vectors, we can signal the matching algorithm that the word drugs and the word pharmaceuticals are essentially similar, semantically similar. And therefore, we should probably consider Eagle Pharmaceuticals and Eagle Drugs as referring to the same organization, or at least to the same name. And there are many such examples. And of course, we can use multilingual vectors so that we can consider such name variations when they're written also in other languages, in different scripts in different languages. Event extraction is another capability. That's a new capability of Rosette. And Rosette is trained to detect patterns of events with building blocks referring to specific roles in the event. So here, for example, we have two texts which describe someone who got arrested by a law enforcement entity. The first one, the word husband, refers to the entity that got arrested. And in the second example, it's the word woman. Both texts have the same pattern, right? And the first one, husband, got arrested by Springfield police. And in the second one, the woman was arrested by U.S. Marshals. And the text highlighted in green referred to the key phrase that was used to detect the event that is described here, the type of the event, which is arrest. Without getting into too many details here about how we implement event extraction, which we can probably cover in another session. Rosette uses text vectors to compare segments of text here in between the roles, between the entities, highlighted in gray here, in order to find similarity between patterns of the same entity type. And using such vectors enables us to find pattern similarity or event pattern similarity in a very efficient way. Document similarity is another relevant use case using text vectors, as I showed you before. Text vectors represent the text written in a document, right? So one vector per document, and so you can use those vectors to now to use a document as a query, right? The same way we did with the word noisy, but now you can just type in content of a document, and then you can look for similar documents in, let's say, a large folder full of documents or a database. This tool is something that we call Semantic Studio. And as for example, you can see here when I type in here, after quitting the deal, United States imposed new sanctions on Iran. So it's talking about those topics, and you can see in the results, relevant documents, at least based on their title. And on the left side here, you can see the semantic similarity score that was calculated for every document using the query that we can see here. So there are more use cases that I could cover here, of course, but we are running out of time. So I'll probably just mention one obvious use case, which is Rosette's semantic similarity endpoint, which is available to use. It's where you can submit text and then retrieve its text vector. It could be a single word, it could be like a just text of a document. And we can also use this endpoint to find the K most similar word from a large vocabulary that we maintain in many different languages. Okay, so thank you so much for attending this session. I hope I could give you some information about word vectors and how they're created and how they're being used, and above all, why we need them, right? So very happy to take any questions. Thank you so much.
Thanks, Kafir. That was great. Really, really interesting discussion. We do have a couple of questions that came in through the chat. The first one is, does Rosette rely entirely on off-the-shelf models, or are there some applications where curated data sets may also be used?
Okay, great question. So yes, Rosette, first, Rosette has different capabilities. I showed that in my last slide. And each capability is usually shipped with an off-the-shelf model that we train here for different languages, using our own data. However, most of our capabilities come also with a training kit, which you can use for fine-tuning a model, an existing model, or you can even use those to create a model from scratch.
Thanks. Next one is, what are some of the broader use cases for semantic similarity where word embeddings are most useful?
Okay, so yeah, maybe something that I didn't mention before, and which is very important for semantic similarity or for word vectors, right? It's so basically NLP. Almost every NLP task is addressed by a neural network, some sort of a neural network, which is a mathematical device, right? And in order to introduce text to the network, we need to convert the text into a mathematical representation. So using word vectors, it's just it's very easy to do something like that, right? So basically, we take the text, we convert the text into like a collection of word vectors, or into a single vector, or something else that we decide, whatever we decide to do, but it will involve some vectors in that representation, and then we can introduce that to the networks, and that was shown to be very effective. So basically, like with every NLP task that we use a neural network, we are using word vectors. So I would say that this is the broader use case, I guess. And I'll also mention, a use case for semantic similarity. I think the task that we covered today in today's session, which is search, right? Semantic search, I think that is one of the most important fields that can benefit from using word vectors.
So the next question is, what type of language objects give semantic similarity the most trouble, and how do word embeddings help solve the problem?
Yeah. Okay. So I think one Yeah, so I'll mention something that we covered during our presentation. So we talked about text vectors, and it's when we represent a document with one vector, right? And then we had to aggregate those the individual word vectors into a single one. There are many challenges there because words are, they get their meaning gets modified by adjacent words. Using this simple aggregation, as I showed before, might raise some challenges and the representation might not be accurate. So definitely generating good text vector is definitely one of those challenges. But I'm also thinking about another challenge or difficulty in using word vectors. So we talked about, generating word vectors for like a single vector per word, but a word may have, different meanings, right? Like different senses. In linguistics, we call this polysemy, right? So if you think about this, the word bank can be like, the side of a river. It could be also a financial institute. But you only have one vector to represent it. So it depends what corpus you use to generate this vector. If that corpus will have more financial documents, I guess you will get more of that relevant sense in this representation or final representation, right? But then when you use this vector, you can use it in different contexts, and that's definitely a challenge. So there are different ways to handle that, of course. And one of them, of course, is using a more dynamic approach for generating vectors, but probably going to leave that for another time.
Well, it sounds like you need to have a very specific vocabulary for the area that you want to analyze. So if you were a geologist, for example, you'd want something that had to do with rivers. And if you're a financial expert, you want to have a corpus and a vocabulary that focuses on financial terms.
Yeah, correct. Yeah, that's definitely going to help.
Yeah. So the last question that came in, this one should be interesting, which is, given now the emergence of the Chat GPT model, what is the future of word embeddings? How do you see that?
Yeah, that's definitely a good question, and I'm thinking about this a lot recently, and not just word vectors, but NLP in general. So obviously, ChatGPT and all those similar models, they're changing the way that we think about how to solve NLP tasks, right? How to build algorithms that handle those known tasks, including semantic search for sure. But as I said before, I still think that we're still in learning mode, right? And there's there are many challenges with bringing those models into into the production, into a product that can go and then we can install it in on site, especially referring to those computational challenges that I mentioned before. So we're still not there in that sense, and I think one way to continue or exploring this field using ChatGPT and other relevant models is to explore ways of how to make them like smaller or lighter, right? In the way that they they consume computational power. And that's very important, and that's definitely challenging because this is the whole point of these models. They are large, so they have a lot of information that is encoded into their weights, and we need to learn and explore ways for how to compress that information. And this is something that we are at Babel research team is working on as we speak. And obviously, as I said, we're continuing to learn this field and to monitor it closely.
Great. Well, thank you again, Kafir, for your time, and we really appreciate this information. Did you have any last words you wanted to say to our audience?
No, thank you so much for having me and for staying with me. Yeah, thank you.
Thanks very much. Bye-bye.